Hi, I'm Kenny Jones, and today we'll be presenting ShapeMOD, macro operation discovery for 3D shape programs, which is joint work from Brown University, Adobe Research, and University College London. Procedural representations are prevalent across many different computer graphics applications. For instance, shader programs are used to flexibly render complex visual scenes through clever combinations of much simpler mathematical functions. In vector graphics, compositions of parameterized shape primitives form procedures that allow designers to easily manipulate semantic attributes of output images. And for 3D shapes and scenes, grammars can compactly represent families of related objects in an interpretable and editable representation. So what makes a procedural representation useful for a given application? Programs are powerful because they can capture complex behavior in a concise, human-readable form. Short, well-written programs are what make many procedural representations easy to work with and manipulate. In order to achieve these desired properties, programs rely on abstraction. For instance, subroutines are employed to consolidate common patterns of code use. However, it is difficult and requires domain expertise to define the right set of abstractions for a given domain. In this talk, we explore how to discover such abstractions in an automatic fashion. In this presentation, we focus on 3D shape programs as an application area, but the ideas we'll present should be applicable to other procedural domains, and we'll come back to them at the end of the talk. There's a rich tradition within computer graphics demonstrating the value of programs for generating 3D data, from plants to furniture and even buildings and cities. As a representation, shape programs offer the ability to generate high-quality outputs by construction, and their form allows for direct and intuitive editing. However, using programs to represent 3D shapes also comes with limitations. The main downside of 3D shape programs is that they are difficult to create. Authoring a shape program requires domain expertise, and it's arguably more labor-intensive than creating a single 3D model. This difficulty rises as the quality of the program improves. Care must be taken so that the exposed parameters are easy to interpret and edit. Hence, the best procedural models often make use of function blocks and subroutines. Additionally, while some procedural representations can capture families of closely related shapes, these can be even more difficult to author, and the variability of the outputs is still fairly constrained. Recent works have begun to investigate approaches that mitigate the limitations of the shape program representation by, for instance, learning to automatically generate programs of 3D data. At SIGGRAPH Asia, we presented the ShapeAssembly language and method. ShapeAssembly's domain-specific language, or DSL, represents 3D shapes by defining parts abstracted with bounding cuboids and attaching parts to one another in order to form complex 3D shape structures. ShapeAssembly demonstrated that deep generative models could be trained to write 3D shape programs. This paradigm maintains the benefits of shape programs as a representational form, but the limitations are mitigated as programs can be automatically authored, and the outputs can contain a high degree of variability by exploring the latent space of a learned model. ShapeAssembly's DSL contains both base functions and macro functions. We define a macro function as one that, when executed, expands into a series of commands from the base DSL. For instance, the squeeze macro from the ShapeAssembly DSL expands into 2 attach commands at execution time. To maximally realize their representational benefits, shape programs should be compact, while still exposing important degrees of freedom for editing. Introducing macro operations that abstract away common patterns of use can help achieve such properties. In fact, ShapeAssembly showed that representing programs with macros actually improved performance on downstream learning tasks, such as novel shape generation. However, these macros were carefully and manually designed by domain experts, and they might not generalize or be useful for other shape modeling domains. Ideally, the system would be able to author programs similar to those that humans produce, using subroutines to expose only a small number of meaningful parameters, but without relying on domain experts to provide the intermediate abstractions. This realization raises the question, can useful macros for a given shape modeling domain be discovered automatically by an algorithm? There's been some past work that attempts to find program rewrites to improve a single program of interest. Within the domain of shape modeling languages, the Selinsky system takes a low-level CAD program as input and searches for a more compact, higher-level program which produces the same output geometry. The Carpentry compiler finds rewrites of low-level instructions that maintain high-level semantics while optimizing to reduce manufacturing cost. While these methods work well for single shape instances, they are unable to discover macro operators that are useful across a collection of shape programs. Our macro discovery goal is one instance of a more general class of problems, finding common abstractions within a set of programs. Within shape modeling, there's a rich history of research on grammar induction, but most work on this problem has focused on solutions specific to context-free grammars. More broadly, some techniques have been proposed that are able to find abstractions for general functional programs. Dreamcoder is one such recent algorithm that uses wake and sleep phases in a successive fashion to first find programs that solve input problems and then identify abstractions common to the set of discovered programs. For example, on list processing tasks, Dreamcoder first discovers a macro corresponding to the common filter function, and then discovers a maximum function, which uses this filter function as a subroutine. However, these algorithms are designed to operate on functional programs, and as such, are not suited to imperative shape programs, where lines can only be reordered in certain ways to preserve program validity. Moreover, while they do provide support for real-valued free parameters, they are unable to discover parametric relationships between continuous variables. Concretely, we desire a system for automatically discovering macro operations with the following properties. It should be able to handle languages beyond simple context-free grammars. It should discover macros that can be broadly applied across collections of programs. It should be able to handle line reorderings of imperative programs. And finally, it should discover macros that capture the salient parametric relationships between continuous variables. As no previous method fits this criteria, we designed and now present our approach to solving this problem, macro operation discovery for 3D shape programs, or ShapeMOD for short. ShapeMOD takes as input a dataset of 3D shape programs. It discovers macro operators that make programs more compact by minimizing the number of function calls and free parameters needed to represent the entire input program collection. The input programs can be rewritten with these macros, which improves performance on downstream tasks such as novel shape generation. Additionally, discovered macros expose only a small number of parameters, facilitating shape editing. Here we show one such discovered macro that we name 4-leg base, as it is used to represent regular chair bases. It exposes only 2 free parameters, one that modifies the leg sizes and one that modifies the leg's positioning. ShapeMOD is initialized with a dataset of programs and a library of DSL functions used to express them. It aims to find a new library, augmented with macro functions, that is able to express the dataset of programs in a more compact fashion. When deciding which macro functions are best suited for a dataset of programs, there is an inherent trade-off between program compactness and program usability. On one extreme, no macro functions could be used, allowing each program to maintain maximal flexibility, but sacrificing program compactness. On the other extreme, a macro function could be created for each program instance in the dataset. This would offer the maximum amount of compression, but each program would become so specialized that editing would become impossible. Our intuition is that good macros balance the trade-offs between these two extremes. We want to find macros that can be applied frequently across a collection of programs, removing parameters that correspond to extraneous degrees of freedom, without removing necessary degrees of freedom that allow for meaningful shape manipulations. We quantify how ShapeMOD should navigate this trade-off with an objective function that computes a weighted average between program compactness, that is, the amount of free parameters needed to represent the dataset, and the number of functions in the library. Now, we're going to talk about how this box works. As minimizing the objective function is NP-hard, we take a greedy approach. The ShapeMOD algorithm has 2 phases. First, a proposal phase analyzes clusters of similar programs and uses the clusters to propose a set of candidate macros. Second, an integration phase ranks and iteratively evaluates these candidate macros, adding them into the current version of the library whenever it would improve the objective function, and refactoring the dataset of programs to be rewritten with the discovered macros. These 2 phases can be alternated to gradually grow the discovered library with more complex macros. Our 2-phase approach is inspired by the wake and sleep phases from Dreamcoder. ShapeMOD's proposal phase creates a large set of candidate macros that may help to improve the objective function. It begins by picking a program at random out of the dataset. We represent each shape program by its program lines and the collection of valid orderings of those lines, that is, only the orders that create the correct geometry when executed. Using the sampled program as a seed, we then form a cluster of structurally identical programs by finding all programs that match on structural elements, shown in yellow, and then sampling a subset of matching programs based on parameter similarity. Next, we find a single abstracted program that is able to represent the majority of programs in the cluster. An abstracted program is one whose functions are parameterized with a mix of free parameters, constants, and expressions over other parameters. We construct the function calls of this abstracted program through a greedy search over the library and find parameterizations for each function by iterating through a heuristic preference ordering. Please refer to our paper for details. Once we've found an abstracted program, we identify subsequences of lines, shown in green, that could be converted into standalone macros. In the last step, we take the set of candidate macros and add in any macros that are generalizations of this initial set. One macro generalizes another macro if it can produce a superset of the other macro's outputs. For instance, the middle macro generalizes the top macro by replacing a shared constant expression in gray with a new free variable in blue. The integration phase decides which candidate macros should be added into the library according to the objective function. First, the integration phase heuristically ranks the large set of candidate macros according to an estimate of how much each macro is likely to improve the score of the objective function. Then, the top-ranked macro is removed from the candidate set and combined with the current version of the library. Under the new library version, ShapeMOD searches for the best program rewrite for each program in the dataset in order to minimize the value of the objective function. ShapeMOD then calculates the objective function score of the original library in the new library. It accepts the new library if it leads to a better objective function score. Otherwise, the macro under consideration is rejected and the old library is kept. This process is repeated for multiple top-ranked macros. The proposal and integration phases can be run iteratively for multiple rounds in order to discover increasingly complex macros with hierarchical relationships. For instance, macro 1 in green was discovered during the first round, and then it was used as a subroutine within macro 2 in purple discovered during the second round. We experimentally evaluate ShapeMOD's ability to discover useful macro operations by running it over collections of ShapeAssembly programs representing various categories of manufactured CAD shapes from the chair, table, and storage furniture categories of PartNet. ShapeMOD discovers macros that help condense programs and remove extraneous degrees of freedom. Here, we illustrate this process for some programs from the tables dataset. We run ShapeMOD over the collection of input programs to discover a library of macro functions. ShapeMOD can then find rewrites of the original programs using the discovered macros in order to remove extraneous degrees of freedom, performing corresponding program edits to the original programs without macros, and the refactored programs with macros demonstrates the benefit of ShapeMOD. The discovered macros capture parametric relationships that better preserve shape plausibility under manipulation. For example, after the sequence of edits, all table legs remain the same size in the third column shape that uses macros, while the shape in the fourth column that doesn't use any macros becomes disconnected and physically implausible. We validate that the ShapeMOD algorithm is effective at optimizing the objective function. For each data set of programs, we compare the starting objective function value, the final objective function value found by ShapeMOD, and the final objective function value found by a baseline method that takes a naive single-pass approach to discovering macros. ShapeMOD does the best job of minimizing the objective function. We also investigated if learning on programs that have been refactored to use macros improves performance on downstream tasks. The first task we examine is novel shape generation. We make use of the deep generative model architecture from ShapeAssembly. Here we visualize some programs written by our learned generative model that contain discovered macros. We compare the quality of generated outputs when trained on a dataset of programs with and without the discovered macros. We evaluate the percent improvement on the same metrics used in the ShapeAssembly paper, measuring their plausibility with the percent fool and for shade distance metrics, and their physical validity with the percent rooted and percent stable metrics. As shown, learning over datasets of programs that use macros improves the quality of the generative model. We also evaluate the impact of macros on the task of visual program induction, inferring a shape program from unstructured geometry. We train networks to perform this task in an encoder-decoder fashion, leveraging a PointNet++ to encode point clouds and reusing the program decoder from the novel shape generation paradigm to turn a latent code into a program. We compare reconstructions from models that were trained on programs that didn't use macros with reconstructions from models that were trained on programs that did use macros. Across all categories, we find that learning on programs that use macros increases both geometric reconstruction accuracy and physical plausibility of the inferred shape structures. Visual results confirm the quantitative trends. To examine the specificity of discovered macros to particular categories of shape programs, we also experimented with a cross-category paradigm, where one set of macro operations was discovered across a combined dataset of chair, table, and storage furniture programs. Comparing ShapeMOD macros found in the per category and cross-category paradigms, we found that interestingly, the cross-category paradigm discovers a library of functions that better optimizes the objective function. This demonstrates that ShapeMOD can discover macros that identify shared structures across different but related program datasets. For the other downstream tasks, although we observe it is slightly better to run ShapeMOD on a per category basis, the marginal performance gap between the two sets of macros gives a strong indication that the types of macros ShapeMOD discovers are capable of generalization. For our final downstream task, we evaluate if macros make shape programs easier to edit with a user study. Our experiment had two conditions: whether users edited programs that contained or did not contain macro operators. We built an interactive editing interface for the user study. Participants were asked to complete a series of goal-directed editing tasks, modifying the continuous parameters of the ShapeAssembly programs through sliders in order to match a target output shape as closely as possible. Here's a video of what that process looked like. Now we show how ShapeMOD macros facilitate shape editing. On the top row, we show the initial program output in gray and a target shape in yellow for each task in the user study. On the x-axis, we plot the time elapsed, and on the y-axis, we plot the similarity between the executed shape of the edited program and the target geometry, where lower numbers mean they are more similar. The orange lines indicate edit sequences to programs that use macros, while the blue lines indicate edit sequences to programs without macros. For each task, participants using ShapeMOD macros more quickly converged to the target shapes and achieved a closer end fit. So, to conclude, we presented ShapeMOD, an algorithm that automatically discovers macro operators that can be used to more compactly represent collections of programs written in an imperative language that may contain continuous variables. We demonstrated that rewriting shape programs with the discovered macro operators can lead to improvements for many different downstream tasks. The benefits of shape programs are best realized when a small number of meaningful parameters are left exposed. Rewriting programs with macros is one way to achieve this outcome. Automatically discovering macros that are useful across collections of shape programs allows for this outcome to scale beyond expert intervention. There are many exciting avenues of future work within this space. The abstractions that ShapeMOD currently considers when proposing macros are relatively simple refactorings of free parameters, but the algorithm could be extended to consider other types of abstraction operations, such as for loops or conditionals, and in doing so, discover more helpful macros. While ShapeMOD discovers useful macros, it does not assign them semantic names. To see how well the macro ShapeMOD discovers capture semantic properties, we ran a user study asking participants to name the functions and the parameters of some ShapeMOD discovered macros. The user assigned names for each attribute often cluster around semantic properties. For instance, most users identify the purpose of this macro for creating chair legs, with its first parameter controlling size and its second parameter controlling position. Finding efficient ways to assign semantic names, such as these, to automatically discovered macros would be a fruitful direction of future work. At present, ShapeMOD requires a dataset of programs as input. However, there are not many existing datasets of shape programs. It would be interesting to try extending our method so that it is able to jointly discover macro operations and a dataset of shape programs, given only a dataset of raw shapes as input. Methods that are able to break raw shapes into part proxies, a problem which another paper being presented at our session focuses on, could be very helpful in realizing this goal. While we have to this point only investigated ShapeMOD in the context of ShapeAssembly, the algorithm is quite general. It makes no assumptions about the input language, other than it is imperative and has parameters that adhere to some typing system. We are excited to see how ShapeMOD could be applied to other problems expressible in such a language, such as vector graphics or shader programming. We have a project page for ShapeMOD, which can be found at the listed address. Thanks for listening, and please feel free to reach out for additional information, questions, or clarifications.